Welcome to Rges Algebra 2. This is lesson 22B and the section is 7.1. We're beginning a section on powers and roots. These are our basic operations or rules for powers. X to the 0 equals 1. Anything to the 0 power equals 1. An example would be 3x to the 0. X to the 0 is 1, so that's the same as 3 times 1, which is the same as 3. The next one, x to the 1 power, anything to the first power is 1. I'm sorry, try that again, is x, the same thing. So if I had x squared y to the first, well, let me give you a better example for that. Let's see. So if I had 7 to the first power, that would be the same as 7. If I had x to the a power times x to the b power, same variable, different exponents, and I'm multiplying them together, I add my exponents. That would equal x to the a plus b. So an example of that would be if we had x squared y cubed x to the fifth y to the seventh. Same variable, add exponents, my y's, 3 plus 7 is 10. There we go. Next rule, if we had division of the variable with the exponent, we would subtract the exponents. And an example of that would be x to the 7th over x cubed. Subtracting the exponents gives me x to the 4th. Next rule, if we had x to the a raising an exponent, a variable with an exponent, to another power, we multiply exponents. And this example would be let's say I had x cubed raised to the 5th power. I multiply my exponents, that would be x to the 15th. A little bit more review. If we had 1 over x to the a, that is the same as taking it across the division line with a negative exponent. And we can flip that in reverse. If we had x to the negative a, that is the same as making it a positive exponent down below. Extrapolating on that idea, if I wanted to make it a, let's say, one more idea here, if I had 1 over x to the negative a, if I wanted to make that positive, that would equal x to the a. So I think that's enough illustrations over there. Maybe illustrating just a couple more ideas as far as examples go. I said x to the 7th over x to the 3rd. What if I had x to the 3rd over x to the 7th? There's really two ways I can look at it based on the ideas above. I could take the numerator minus the denominator, which is to the negative 4, and that equals x to the negative 4 power. Or I could decide that, okay, I have more x's in the denominator. 7 minus 3 is x to the 4th still in the denominator. And notice from above that these two answers are equivalent. So that would be the practical use of that. One more example, just so we don't get tripped up. What if I had something like x squared over x to the negative 7th? This would be subtracting exponents 2 minus a negative 7, so that would be x to the 9th. Okay, I'm going to go through on the next page some examples to get you started. This is a review lesson, but I just want to make sure our foundation is very good for what comes forward here. So I would recommend that you do these problems maybe 2 or 3 or 4 at a time. And I think I'll do them 3 at a time. And you put it on pause, try to get the answers yourself, and then unpause it and check yourself. Let's do these 3 first. Okay, remember, if we're raising powers to a power, we're going to multiply exponents. 3 times 3 is 9, 2 times 3 is 6 for the y term, and 1 times 3, 3 for the z term. Notice here, this is something that students will tend to get wrong because they're in multiplying mode now. If we're going to square a negative sign, it will be positive. This is the trick right here on the 3. We know how to do 3 squared, but right now we're in the mode of multiplying. Okay, x to the squared, y to the 4th. So we tend to sometimes say 3 times 2, and that's not true. 3 squared is 3 times 3, and so that's where the 9 comes from. So be careful with the numerical part. It's just enough different from the operation we're doing with exponents that students tend to get confused. We're not as used to having a variable in our exponent, but it's the same idea. A is to the first power, so 1 times n is n, 2 times n is 2n, and negative 1 times n is negative n. Let's do the next 3. Okay, oops, don't have an exponent there, sorry. Okay, here's our next 3 problems, so go ahead and put it on pause until you want the answers for those, and then check them. Okay, looking at 4 through 6, because it's an odd power, we'll keep our negative sign. 2, it's not 2 times 3, it's going to be 2 times 2 times 2, 2 to the 3rd power. That's going to give me my 8, and then my exponents 12 and 15. On the next one, again, a negative will retain because it's odd, and 3 times 3 is 9, and then we're going to distribute the 3 through the exponent there, the exponent expression. We'll get 3n minus 6. The last one, because it's even, we know it's going to be positive, and 1 to any power is going to be 1, because it's going to be 1 times 1, or 1 times 1 times 1 times 1 times 1, whatever that would be. Positive like that. All right, so let's look at some more examples. Let me write them down. Here would be your next 3. Go ahead and put it on pause one more time until you're ready to check your answers. Okay, anything tricky here? Let's see. 2n plus 1 as a power. 2n would be even, so 2n plus 1 would be odd. An odd power would make the negative sign retained, and then the rest is just a distribution of 3 across 2n plus 1. Again, an odd power will let the negative sign remain. 2 distributions, 3 times the quantity n minus 1 and 3 times the quantity n plus 2. My last answer here, this answer might be hard to read. It's negative x to the 3n minus 3, y to the 3n plus 6. Kind of went off the board there, sorry. Okay, now for the next one, we're going to cube everything. we're going to follow our exponent rules. So 2 cubed is 8, and x cubed is x cubed. X, the 1, that's the same as 1 times 3. 3 cubed is 27, and y multiplying exponents to the 6th. Okay, notice what starts in the numerator is staying in the numerator. What starts in the denominator is staying in the denominator. The only time that would shift is if I had a negative exponent and I wanted everything positive or something like that. Okay, let's, I think we have 3 more. Okay, here are your next 3 problems. Go ahead and put them on pause until you find your answers, and then check them here. And our last 3 problems, the answers are this. When I have something to the 5th power, I tend to say, okay, 3 squared is 9. To the 4th power would be 9 times 9, 81, and then 81 times 3 more. Okay, negative because it's an odd power. Everything else is self-explanatory there, I think. Okay, when we're raising to the n power, we're going to go ahead and distribute the n through, so we'll get something like n squared, which you haven't seen before, n squared plus 2n. Following through that same idea, we tend to always write our number first and then our letters in alphabetical order for our variables. So that would be b to the 3n in the denominator, x to the multiplying, right, 2a times n, and we'll get x to the 2an power and y to the bn power. On the last one, we're going to be able to make it, I did not do that, but I cut myself. There we go. We're going to make it positive because it is an even power. And so that should be a positive. Multiplying 8n to 2bn, say the number part first and then order the variables. C, multiplying out, we're going to get 2n squared, and d to the 2an. So now, on the next page, we'll go over a couple quick ideas, and you'll be ready to go. First off, I want you to know your squares, okay? Know squares, have them memorized 1 to 15. So I know that you, for instance, would know what 2 squared is or what 7 squared is, but I want you to know 11 squared, 121, right? 12 squared, 144, 13 squared, all the way to 15 squared. Make sure you have those memorized. Powers of 2 to 6. One through 6. What does that mean? 2 to the first power is 2. 2 to the second power is 2 squared, or 4. 2 to the third power is 2 times 2 times 2, or 8. Have these memorized. 2 to the fourth power, remember I said if it's a fourth, I'd multiply 2 squared twice. So 2 squared is 4. 4 times 4 is 16. 2 to the fifth power is 32. And 2 to the sixth power is 64. So you should know all of those very quickly. And the last thing let's talk about is how to do a labor problem. The basic format for a labor problem is to recognize you're going to have several workers. This would be like worker 1, worker 2. They might have names or not, okay, etc. We're going to be concerned about the number of hours they work and about their rate per hour. So this is the type of chart I'm concerned with. The basic idea would be if he has worked if he's worked X hours, his rate per hour is 1 over X. And if the second person has worked y hours, the rate per hour is 1 over y. This is the generic idea and needs to be remembered. Okay, that means for all rate problems, you're going to look at it that way. The third thing that's a little odd about rate problems is that the whole job is going to be represented by the number 1, because the first person does a portion or a fraction of 1, and the second person does a portion or fraction of 1. So when they finish the job is 1. So let's read the example problem. I'm going to do it maybe a little bit different than they do, maybe not, maybe it's about the same. But it says Emily and Mitchell can clean their grandfather's RV camper in 2 hours. So this is going to be Emily, and this is going to be Mitchell. And together, how many hours do they take? We're looking at the first column. They take x plus y hours. Okay, so we're going to add it together. Together they clean it in 2 hours. Okay. If Emily cleans for 1 hour alone, Mitchell can finish the job in 4 hours. So my next equation would look like this. Okay. Well, we're telling me that Emily is 1 hour, and let me write it this way. Yeah, let me write it. Sorry, I thought I'd had that on pause. I apologize. Okay, so back to this. Let's see. If together they're working both together. Emily is working 2 hours in this first scenario. Okay, Emily's working 2 hours, and the part of the job she's getting done, how much of the job, okay, is 1 over x. And whatever it was, Mitchell is working 2 hours, and his part of the job that he's getting done, how much he's doing in every hour, is 1 over y. And all together, they get the whole job done. Isn't that interesting? Okay, so this represents the part of the job she's getting done, the part of the job he's getting done, and all together they get, this is kind of an odd idea, but they get the entire job done. Now with the second set of information, I've got it a little different. If she works for 1 hour and she gets 1 over X part of the job done per hour, that's the rate of the job done, okay, the rate of the job, or the portion of the job. She gets 1 over X done, and then Mitchell comes in, and he is working for 4 more hours, and he gets another part of the job done, however much he gets done per hour, plus multiplied times the 4 hours, and he gets the whole job done. So this is a kind of a squirrely arrangement, but I would say memorize that for labor problems, because I don't think it's the most intuitive thing we would first attempt to do. Now, I'm going to have you go ahead and use U and V to solve this and look at it for the answer. And what we're solving is that Emily, it said how long would it take for Emily and Mitchell each to clean the RV working separately? It would take Emily 3 hours and it would take Mitchell 6 hours. U is yes. Okay. So you go ahead and try those word problems in addition.